Okay, thank you so much, Steve, and thank you all for your attendance. Okay, so my presentation is titled UHPC Fresh Chloride Limit Testing, and here is my outline. I'll be giving a brief background, then I'll talk about the mix design proportion, test methodology, test result, then I'll show my acid and water soluble test result, then we'll give the conclusion. So basically, if we look at the F-dot concrete classes, there is a whole range between the 10 KSI and the let's say 20 or 21 KSI. There is probably a good range of concrete that we will be using in the future, and we are not taking advantage of. So, we thought we would go ahead and do some testing to see the benefit of these mixes, and to show what is how are they different from each other. So usually mixes with higher cementitious materials are prone to exceeding the chloride threshold testing. And when we compare the normal concrete to UHPC, UHPC uses a lot of admixtures. So we cannot ignore the chlorides that is in the admixtures. So when talking about the fresh chloride limit, there is the ACI limit 318, and there is the FDOT limit. So here is the a table that summarizes the ACI 318 limit. And when we see the exposure classes, there is a C0 and C1 and C2. So C0, there is no exposure. And the C1, the concrete exposed to moisture, but not to an external source of chloride. And the C2, the concrete that has a lot of external sources of chlorides. So here is the maximum. Let me just use this one. Or here is the maximum. The maximum water soluble test per percent of cementitious material. For C1 is 0.3 and 0.15. So we have to remember this because we are going back to these results again. So also for the F-dot limit, they limit the chloride percentage to 0.4 pound per cubic yard for the acid-soluble test. So talking about the UHPC, or our mix proportion, the mix is from 12 up to 21. We used almost the same materials. Here, if you see the sand and type 1L cement and the slag and the silica fume, and we played a little bit with the water cement ratio, ranged from 0.25 up to 0.1625 for the 21. For the higher mixes, for the 21 plus, we are including more materials in order to gain more strength. So we include the silica flour and the white silica fume. And here is the mix design for our normal concrete. We are using the higher water cement ratio, 0.44, without any admixtures used. So talking about the fresh chloride limit, what we consider a trace or negligible for the normal concrete that we usually uses the chemical admixture for this normal concrete. It usually happens here at around 3 pounds or 5 pounds per cubic yard. But for UHPC, it's not the case. For UHPC, we are using a lot of admixtures, sometimes up to 60 pounds per cubic yard. So talking about this one, we already exceeded the DOT limit, which is 0.4. So it's different from mix to mix, but usually we are using a lot of admixtures. So then how we test these admixtures? How do we test the chloride in these admixtures? So we have followed a European method. It's called the EN480, version 14, and we made some modification. First, we used the UHPC instead of normal concrete, and then we played with the dimensions of this test, and also we used a king wire for this test. So for, this method is meant for determination of the effect and corrosion of reinforcing steel by potential static electrochemical test. So basically, so here is our sample look like. So we are using a UHP sample, 2x4 inch, and we are using the working electrode as a king wire from a pre-stressing steel, and we are using the epoxy at the top here just to prevent any creasive corrosion. The epoxy we are using is Sika 32, and here is our testing method. Is the counter electrode is stainless steel, and the working electrode, as I mentioned, is king wire, and the reference electrode is silver chloride, and we are using the gamma for this to do the potential and the current. So in short, this test is when we place the concrete, we just embedded a steel or like king wire in the middle. Then we left it for 24 hours. Then we demold it again. And after we demolding it, we put it in lime solution for 24 hours again. And then we test it for 24 hours. So the duration for the whole testing is going to be 3 days. And here is in reality how it looks like. The 2x4 inch concrete, and here is it's like a picture from the lab, the lime solution, the sample inside, and we are using the gamma for that. So after we after we test it, we have added some. So we have added some chloride gradually from 0 up to 10 pounds per cubic yard, and we, as we can see here, when we reach 9 pounds per cubic yard, there is no corrosion. But when we add 10 pounds per cubic yard, there is a corrosion. This is the first one. This is the replicate one, and that means this test is like picks it really well. Looks at the corrosion really well. This is for the 18 KSI mixture. So here is just to demonstrate the corrosion. Less than 10 pounds per cubic yard, there is no corrosion. 10 pounds per cubic yard, we see a corrosion here, and the second corrosion for this one also is here. So here is the corrosion rate for all of our mixes. As you can see here, I mean, the corrosion rate is really different between the 21 KSI and compared to normal concrete. As you can see here, the 20 KSI, it has almost a steady rate, which means that it will have a long surface life, and then followed by 18 KSI, followed by 15, and followed by the 12. And here is the normal concrete. The normal concrete corroded really fast. I think during the first hour. So and the current flow is so too high. Yeah, and I believe the higher the resistivity, the lower the conductivity, and the lower the corrosion rate. It is just to show the corrosion for the 21 plus KSI mix, and here's to see the corrosion for the normal concrete. And so after testing, we looked at the highest chloride levels without corrosion. But if you just look at this number, they are almost the same actually. I mean, 12 pound, 10 pound, 13 pound. So the 0.44 corroded at 12, and the 12, 15 KSI corroded at 11, and 15 to 18 corroded at 14, and that 18 to 21 corroded at 10, the 21 plus corroded at 13. So there is no, if you just consider the amount of chloride that you added to the concrete, there is no difference. But if you consider the amount of leaching that happens during the testing, you will see a big difference. So here is the acid and the water-soluble test, and here is the cementitious material, and here is the measured total chloride acid-soluble, and the water-soluble. Again, we see no difference between the water-soluble chloride per pound per cubic yard. If we are talking about the per mix now, so there is no difference. But if we are talking about the leaching chlorides after testing, we see that the normal concrete has almost 4 times higher than the UHPC in testing. So in just 2 days, the chloride leaches a lot. So that means we do not need to look at the chloride in concrete during what we added to the mix, but we need to look at the chloride that is during testing. And so the total chlorides required for corrosion was almost 25% higher for UHPC than normal concrete. And this could raise the DOT limit by 25%, is from 0.4 pound per cubic yard to 0.5 pound per cubic yard. And after we account for the leaching, and also we see right now a big difference in the water-soluble. So, but like the water-soluble result per mix, there is no difference. But right now, when we account for leaching and we do it by mass per cementitious material, we can see a big difference between the normal concrete and, let's say, the 21 plus or 18 KSI. So again, talking about the ACI limit, they limit per mass of cementitious material. The C1 is 0.3 and 0.15 for the C2. And I mean, theoretically, you would get a corrosion here in these mixes. If we follow the ACI limit, that means we are having an active corrosion for the 18 and the 21 plus. And we are almost there for the 12 and the 15 KSI. That means we believe that the ACI limit are a bit non-conservative when talking about the UHPC. So probably we need to look back again to these numbers to account for the UHPC samples. So in conclusion, the chloride binding of fresh chlorides in UHPC is similar to normal concrete by percent of cementitious material, and the ACI chloride limits as percent of cementitious material are non-conservative for non-pre-stressed concrete. So also for the FDOT spec of 0.4 pound per cubic yard could be increased by 25% up to 0.5 pound per cubic yard with the same safety factor, while maintaining the same level of safety factor. Acknowledgement that for funding this project, and thank you so much for your listening.
Thank you, Ray.